Do you know what day it is? It's Thursday. That was my lightning, all right? All right, well, a little rain outside, but I don't see any lightning right now. Thor must be just feeling kind of moody, I guess. So, Thursday, May 28th. What are we going to do today? Hey, we're going to talk about some basic wave vocabulary. Okay, what's a wave? Here's a wave. So, what is a wave? A wave is an energy disturbance. Okay? There's some energy, and the energy is going to move from point A to point B. How's it going to get there? Well, you know, energy could move by colliding from particle to particle, like conduction, or, you know, we could take this ball and throw it, and the energy goes with it. That's really kind of what convection does, is matter moves around. Or the energy could move without moving the matter. That's where waves come in. There's another word called medium. Medium is the physical environment through which the wave travels. Right now, I'm talking to the camera, I'm talking to you, and there's sound waves that are traveling through the air. Now, sound waves can travel through the air, sound waves can travel through liquids, sound waves can travel through solids, but you know, if we sucked all the air out of this room, you would... All right, I put the air back in the room. See, when there's no air in the room, you can't hear any sound. Sound requires a physical medium. Water waves require a physical medium. You can't have water waves without the water. Light doesn't require a physical medium. So electromagnetic waves are just a vibration in what's called the electric field and the magnetic field. They don't require an actual substance. The medium is this environment through which the wave travels. Okay, so a couple of basics. Let's just imagine, the easiest one to picture is to think about ripples on the surface of water. So if there were no disturbances, the water would have just this flat appearance. That's called its equilibrium position. So we're getting some vocabulary, right? Just that relaxed position where there was no disturbance is called equilibrium position. And then when we give an energy disturbance, we're going to have high points and low points, right? So the high point of a wave is called a crest. This is vocabulary. And the low point is called a trough. And just look at that. I can imagine a trough shape there. You know, a trough, that's what you feed pigs in. You slop the pigs in a trough. And yeah, this could hold some goodies for our little piggy. Okay? So we got crest and trough, crest and trough. Now, the amount that the material, in this case the physical medium, is moved from equilibrium position is called its displacement. You know, we've used the word displacement before. It's the straight line distance that something's moved. Oh, okay. And the maximum displacement for a given wave is called its amplitude. Okay. Maybe you're practicing to play guitar, and if you're doing an electric guitar, doesn't do much unless you have an amplifier. And the amplifier takes the waves, makes them bigger, right? Bigger displacement. The distance from a point on one wave to the identical point on the next wave is called the wavelength. Now notice the last part of that word is length. Yes, it's a distance. It's a length. So we could measure that in meters. If that's appropriately sized. You know, maybe a smaller wave we might measure in centimeters, or maybe we might measure a wave in nanometers. What kind of wave could we measure in nanometers? Light, the visible light that you and I can see, the wavelength will be measured in nanometers. The symbol for wavelength is a Greek letter. It's a Greek letter lambda, lowercase lambda. and it looks a little bit like an upside down Y. It's got a little squiggle on top. All right, so get used to that. Wavelength is lambda. Then let's see, here's something that we can't put on the diagram. You can't just point to and say, hey, that's the frequency. For the frequency, what you have to do is look at how many waves travel past a point per time. Number per time. If you do that, your label is going to end up being per second, or seconds minus 1, or hertz. Brought that up yesterday. I think it was yesterday, maybe it was the day before. All right? We could, because whenever I talked about frequency this last time, I was also talking about period. Period and frequency are inversely related. So the frequency is the number of waves per time, but the period is the amount of time for one wave. So with water waves, as the energy is moving this way, the water moves up and down this way. And when that happens, it's called a transverse wave. The direction of motion of the medium is perpendicular to the direction of motion of the energy. There are also something that we call longitudinal waves. And that's as the energy is moving this way, the medium vibrates this way. The medium vibrates parallel to the direction of motion of the energy. A little harder to draw. So let's imagine these lines represent the equilibrium position of air molecules. And as I'm speaking, my vocal cords vibrate, and as they vibrate, they push out, say, and push some of the air closer together than it normally wants to be. And that's going to push on the next, and that's going to push on the next, and that's going to create this ripple that travels out. Well, once that place where they're compressed together moves out, then behind that gets left an area where the air molecules are further apart than they normally want to be. And so, as the wave is traveling this way, the air molecules are traveling this way. Okay? The disturbance just goes by, and as the disturbance goes by, the air molecules vibrate a little bit. And the vibration is parallel to the direction of energy motion. Now, the place where these are close together is called the compression, and the place where it's spread apart is called the rarefaction. Rarefaction. It's a weird word. Okay? Sometimes what happens is when people are trying to describe this, they just, to make it easier to look at, they replace the compression with a crest, and they replace the rarefaction with a trough, and so they'll draw in the wave kind of like we're used to seeing it, but the motion isn't that direction. The motion is, so I remember a couple of guys back in high school when we were talking about waves, and they, you know how you do the wave at a football game, and you woo, and it goes around, okay, and it really does look quite like a wave. Well, they were doing the wave, but they were just lined up with hands on shoulders, walking down, compression, rarefaction, compression. A little weird, but interesting science joke. Okay, so there's longitudinal waves. Let's talk about wave velocity. The velocity of a wave is equal to the frequency times the wavelength. Think about the labels of this. Frequency is measured in per seconds. The wavelength might be measured in meters. And so if you put that together, you got meters per second. That's a velocity. Yeah. Just frequency times wavelength. So let's practice that. Let's just say that I had a wave that had a frequency of 23.7 hertz and a wavelength of 1.56 meters. I don't know if that's even possible. I don't know what kind of wave that would be, but if that were my frequency and that were my wavelength, I'd say velocity is frequency times wavelength, and my frequency would be 23.7. Now when I see hertz there, when I come down here, I'm just going to put per second. And I'm multiplying by my wavelength, 1.56 meters per second. Okay, and so this wave is traveling 23.7 times 1.56 equals 36.97. So really it would be 37.0 meters per second. Let's say I have a wave that's got a frequency of 95.5 megahertz, and it's got a wavelength of 3.14 meters. Let's find its speed. So velocity is frequency times wavelength, and the frequency is, all right, what does mega mean? Well, mega means million, right? So what I could do is say this is 95,500,000. Why am I writing that on the bottom? See, this is why we write stuff out though, is because then you catch mistakes. 95,500,000 hertz, and a hertz is per second. And then I got 3.14 meters. So I'm going to get a speed in meters per second. 95,500,000 times 3.14 equals 2 point. Well, with 3 sig figs, it'd be 3.00 times 10 to the 8th meters per second. Ladies and gentlemen, boys and girls, that's the speed of light. This is not just a coincidence. I've done this math the other way around. This is a radio wave. 95.5 megahertz is WIFC in Wausau. And radio waves travel at the speed of light. So I already knew this, and I had worked it backwards to find out what the wavelength is for WIFC's signal, 3.14. I always thought they should advertise themselves as the Big Pie. You know, we got the station in the area called the Big Cheese. They could be the Big Pie. 3.14 is their wavelength. Not that anybody would get it, but I'd like it. All right. I'll give you a couple questions. That's it for today. See you tomorrow.